Okay. I'm on.
Yep.
Tonight's guest speaker is Dr. Lucianne Walkowicz, an astronomer at the Adler Planetarium in Chicago, where she studies stellar magnetic activity and its influence on planetary habitability. She was past Astrobiology Chair at the Library of Congress Kluge Center, co-founder of the JustSpace Alliance, TED speaker, and a practicing artist. Please welcome Dr. Walkowicz.
Hi, everybody out there. And hello, especially to all of the members of the New Jersey Astronomical Association and anybody else who might be watching. The last time I got to give a talk to you all, I was able to visit in person. This is, moderately less good, but good in different ways. So I'm going to share my desktop here. Let me just pull up my slides. And can everyone see that?
Yes.
Yes, great, wonderful. All right. So today I am going to give you a talk about the Vera Rubin Observatory. And this is a telescope project that I have worked on for nearly my entire career in astronomy. I started working on the Rubin Observatory actually when I was a graduate student in 2006.
Wow.
And you'll find out why when you see the massive effort that it takes to make this amazing observatory, which is still in progress. So this is very new things, but it'll be on the sky in a couple of years. And I hope you'll be as excited by the end of this talk as I am. Just to tell you what I do with the observatory, I am the director of what's called the LSSTC Data Science Fellowship Program, which is an educational program I started with a friend and fellow astronomer, Adam Miller, and it teaches data science skills or advanced computing skills to astronomy graduate students. I'm also a member of the Rubin Observatory Science Advisory Committee, but I've held various roles with Rubin over the years, including chairing the science collaborations, which I'll mention in a moment. And as John mentioned at the beginning, I am an astronomer at the Adler Planetarium in Chicago. Oops, it will not let me, there we go, okay. So, for many years, I love this old engraving because it shows how many of us experience the night sky. It is, of course, wonderful to be able to observe the night sky from wherever you are, even if you're in the city of Chicago and you only get a couple of very nice planets, maybe a few stars. But if you have a beautiful night sky where you are, I hope you will spend some time looking at it. But it's very hard to perceive depth, for example. So it often looks like the night sky is just the stars and planets painted on this dome overhead. And so I love this old engraving because it shows how astronomy is really, in some ways, the curiosity to think about lifting that curtain or looking beyond what the sky appears to be to sort of observe all these cycles around us, which will really be a theme when we start talking about the observatory. So you can see the astronomer here giving it a shot and seeing all of the things whirling and twirling on the other side of the curtain. But of course, this is now many hundreds of years old. And today, and for several decades, in fact, we've had amazing images like this from the Hubble Space Telescope. And I love using the Hubble because it is a wonderful example of not only our ability to perceive more deeply into space, more greater detail, the beautiful colors, even though the colors are enhanced in many of the Hubble images to show various features, they still do code information about the universe into them. So we have pictures of like the Eagle Nebula and many other objects where you can see gas and dust in addition to stars. And one of the things that I like starting with the Hubble Space Telescope, the reason that I like starting with the Hubble Space Telescope is that this was not just revolutionary for astronomers, right? The Hubble is an example of a telescope where, because it is a NASA mission and it is something that you essentially pay for with your tax dollars, all of this data is public, right? And so these images that you see from the Hubble Space Telescope have diffused out into pop culture. And so, while these were revolutionary for astronomers, they were also really revolutionary for, I think, a lot of people's understanding of space if they've had the pleasure of seeing these images. And this is, I think, wonderfully true when you see how it can even show up in unexpected places. So I will play you a small clip.
This is going to be a great night tonight.
Yeah!
I'm sorry. Who said that?
I said it. Hey, man, your show is good. Matter of fact, your show is great, but you know what's greater? The exquisite interstellar photography you get with the Hubble Space Telescope. Y'all love that Hubble telescope, right?
The Hubble Space Telescope. Wait, are you really? Are you serious?
Yeah, man. When it comes to vibrant images of celestial bodies and the various celestial bodies that make up our universe, I mean, nobody's got your back like the Hubble Space Telescope. You need an image of the Orion Nebula? Hubble got you. You need an image of the galaxy cluster M0735? Hubble got you. You need an image of the massive star Canis Majoris? Hubble got you. Regular ass Jupiter.
All right, yeah.
So I play this clip, obviously, because I love it. That's Milky J with the Hubble Got You sketch on the Jimmy Fallon show. But it just shows how you can even make a joke on late night TV about like how amazing the Hubble Space Telescope is, and everybody knows kind of what you're talking about. And this just goes to show that like technology is not just amazing for, or new technology is not just amazing for astronomers, it's also, I think, transformative of how we understand the world around us. Now, the only perhaps flaw with the Hubble Space Telescope and other telescopes, that are like it, maybe the last, several decades of modern astronomy, we've gotten more detail, clearer images, more ability to see deeply into space, but we often miss out on is the ability to observe through time. Now, we've always had the idea that the universe is a dynamic place. I'm showing here Starry Night by Van Gogh, where you can see sort of the motion and dynamism that he perceived within the universe captured here in a form of art. And on the left, this is actually observations of Jupiter's moons by Galileo, where you can see a little circle, which is supposed to be Jupiter, and these little asterisks that are supposed to be the moons. And this is him puzzling out over time that these little dots were actually moving around Jupiter in his observations, even with a rudimentary telescope. So time has been, or the ability to observe time has been very important for our ability to understand the universe and its workings, since after all, some of these observations were crucial to our understanding of the fact that the Earth was not the center of the universe. Now, when we observe the night sky close to Earth, often we can observe that there is motion in some ways. So in this case, these are images of the aurora, or movies rather, of the Aurora Nebula, but you can see that they appear to be on kind of this fixed background of stars. So the actual more deep space, the deeper you go into space, the more difficult it is to see that things actually do change and move, because the timescales and distances that we're talking about are so much greater. But as we know, a picture can only tell you so many things, even if it is worth 1,000 words. So in this case, for example, is the wedding cake broken because the marriage is off and the bride stormed out? Or is it because like the reception was so amazing that the cake got knocked over? How did this happen? With just a single image, you don't really know. Now, of course, for the rest of us, it was really video, or the ability to take repeated images over time, that helped us understand things in our world. And video is always so much more informative because of the context it provides and the detail it provides, rather than a single image. So even though there has been the idea of taking what are called time series or repeated images in astronomy, it's been really hard to do this on a large scale, because you have to observe a particular part of the sky or a particular object and really spend a lot of time kind of staring into space. Now, that can be great for learning certain things. For example, it was really wonderful for the Kepler Space Telescope, which found a lot of planets by observing changes, but just in one patch of the sky. But if you really want to understand the universe, you would probably want to be able to do this over a large fraction of the sky, to really be able to map out the night sky, not only across space, but through time as well. And that is the goal, essentially, of the observatory, which I'm going to be speaking about to you this evening. The Vera C. Rubin Observatory, which is shown in artist conception here, and which I will show you some pictures of in a moment. The Vera C. Rubin Observatory is named for this groundbreaking astronomer, Dr. Vera C. Rubin. Dr. Rubin was one of the discoverers of dark matter and has been just a hero to so many people in astronomy that I know. Now, you may actually have heard about the Rubin Observatory previously by its previous name, LSST. The original name of the telescope up until just the beginning of 2020 was LSST, or the Large Synoptic Survey Telescope, which was essentially a kind of placeholder for the telescope name for a long time. So you have to, when you're planning a telescope, you have to call it something so that everybody can refer to it. But I think we all had the idea that this would eventually change, and it's a wonderful thing that it is named for Vera Rubin. Also, just as a side note, one of the reasons I'm happy that it's changed, aside from honoring Rubin's legacy, is that no astronomer seems to know what synoptic means. It means all encompassing, but everybody seems to think it just means the time thing. Anyway, we don't call it LSST anymore. We actually call what we do with the observatory LSST, just to retain the acronym, but it now stands for the Large Survey of Space and Time. So when you refer to it, you could call it Rubin Observatory or just Rubin, but never call it VRO, because then you take the Vera Rubin out of it, and what fun is that? So I'm going to tell you a little bit about the survey, which means what we do with the telescope. I'm going to tell you about the telescope itself and the camera, and then also at the end, the data that we expect that it will produce. So this legacy survey of space and time, or LSST, is what we do with the telescope, the Rubin Observatory. And in sort of a single sentence, you can think of this as a survey of 37 billion objects through space and time. So the telescope will do this by essentially every few nights observing the entire night sky, and then doing it again and again over the course of 10 years. So in a little bit more technical language, because I know we have some really dedicated, very technical observers who might be watching, but this is an optical and near IR survey of UGRIZ bands to a depth over time of 27.5 in our filter. And our filter is sort of right in the middle of where your eyes are sensitive to. So if you're just a human being trying to fathom that, it is very, 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 very sensitive. So that means that you can see more deeply into space. And that means that because you're essentially looking back in time, the more deeply you look into space, it means that we'll be able to see further into the history of the universe. But also because you're doing this thing where you're tiling over the night sky every few nights over 10 years, you will also get this time dimension where you'll see how things change. Now, the Rubin Observatory has been the essentially the highest priority for ground-based observing in the United States, because it has these sort of 4 science objectives that really encompass a lot of astronomy. And they are mapping out and understanding the dark universe, understanding the transient universe, which means the parts of the universe that change with time that is observable to human beings, taking an inventory of our solar system, so not just the planets, but all of the dwarf planets and smaller bodies that exist within the solar system, mapping those out, understanding their orbits, and also mapping our home galaxy, the Milky Way. And this has been an investment of things like the National Science Foundation, the Department of Energy. Some of the independent donors are listed here, also the Stanford Linear Accelerator Center, Aura. All of these agencies have come together to invest in this observatory because it is so helpful to so many aspects of astronomy. And really, it's not just the agencies investing in it, it's also that people everywhere have been working on and anticipating the Rubin Observatory. So I'm just showing you a handful of the member institutions, and also internationally, we now have participation from a huge number of countries, over 20 different countries and different institutions within it. And if, you know, these are just the sort of institutional names or like the national names, but really, this is a community of thousands of astronomers that already work on an observatory that hasn't even started being on the sky yet. And the reason for that is that it will do so many different things that it really takes the entire community to be involved in the design and building and preparations for Rubin Observatory to be on the sky. Thousands of these astronomers work within what we call the science collaborations, and these are topical working groups. So for example, if you're interested in galaxies, then you could go work in the galaxies collaboration. If you're interested in dark energy or the solar system or the transients of variable stars, any one of these things, these are essentially groups of colleagues that are coming together to prepare the way for this observatory to be online. And this also includes just national groups. So the science collaborations themselves are international, but then because a large fraction of the UK's astronomy community are involved, there's an LSST UK, there's also a Chilean group because the observatory, as you'll see, is in Chile, and also France as well, which is contributing a data center. So it really is very much a global effort. And so all of these people together, it's not just a matter of like building the telescope and building the camera, which is what I'll talk about for most of the rest of the hour. But it's really a matter of getting everybody on board to be ready to do science with this amazing new transformative data. So that could mean preparing to do science by doing research, things that you might want to understand before you start trying to incorporate the new data, providing expert advice to the people who are actually building the telescope. You know, a telescope is a piece of equipment, and you can use a piece of equipment in a lot of different ways. And so understanding what the different scientific trade-offs are, you know, for example, if you're interested in galaxies versus solar system, you might want to use the telescope a little bit differently between those two camps, but you only have one telescope, so you have to come to a common understanding of how you're going to do that. And then you have to provide some advice to the observatory on how that will happen. They also, of course, many of these people are in academic institutions or running educational programs like myself, and they train and educate, they engage the scientific community, they fundraise for their projects. So all of the investment of the Rubin Observatory goes into building the telescope at the moment, and the team of people that are actually have to construct it and put it together, which means that scientists that work on this end up having to find grant funding for themselves. They also develop and implement research inclusion practices and collaborate on software development for handling all of this data. So to give you an idea of what this telescope actually looks like, this is a little model of it here. So the Rubin Observatory is the name for the entire system. The name of the telescope is Charles Simonyi for this. Charles Simonyi was one of the donors who helped with the observatory getting its early start before it had institutional agency funding. And it will be located here. So this is a map of Chile, and on the left, I'm showing you a picture from Gemini Observatories. So this is a mountain known as Cerro Pachón in Chile, and it's a little bit north of Santiago. You can see on the map there, a little arrow pointing to where it will be. The dome that you see at the left is Gemini South. So that's one of the Gemini Observatory telescopes. And I'll point that out again to you in a moment once I show you where the Rubin Observatory is located. Now, just a few years ago, the observatory looked like this. So we got our construction funding. So I remember I said I started working on this project in 2006. So it took a really long time for there to be community support to put this together and to actually get the funds to build the telescope itself. And that's normal because of the amount of the sort of magnitude of the project is really quite a lot. And so you need a lot of community buy-in in order to build something this ambitious. So even just a few years ago, after construction started in 2014, this is, I think, from around 2016 or 2017, maybe a little bit even before then, maybe 2015, you can see that there's not much there. But as of last year, this is what the Rubin Observatory looks like today. And I will say on a personal note that it is very strange and wonderful to be able to show an actual photograph of something that you've been showing artist conceptions of for a lot of your career, as I have. It's really kind of amazing to see this physical building exist today. To give you an idea of where this is, so if you look kind of at the upper right there, you will see a dome in the distance, and then one that's a little bit closer. The one that's a little bit closer is the Gemini Observatory dome that I showed you before. And of course, in the foreground, right over here on the side of Saraguachon that is closest to you in this picture is LSST, or the Rubin Observatory. And you can see this little sort of outrigger dome, which is called the Auxiliary Telescope, which I'll show you a picture of in a moment. Now you might wonder why this telescope is so enormous, and why it doesn't look like that traditional dome shape that, you know, if you look at the Gemini Observatory or even the Auxiliary Telescope, you'll see they have quite a different shape than the Rubin Observatory does. And that's because this has to house not only the telescope, but a lot of the equipment that is required for the upkeep of the telescope. So remember that, you know, a little while ago, I told you that this observatory would be operating its survey for 10 years. And that's just the main survey. You know, we fully anticipate that this will be something that continues lasting for decades and decades. Again, you know, look at the example of the Hubble Space Telescope. The Hubble Space Telescope is considerably more difficult to repair than telescopes that are on the ground. It still lasted a long time, right? So when you want to observe with something like this over long periods of time, you also don't want to have to take it off the sky to do any kinds of repairs. You know, it's not exactly convenient to get large pieces of telescope glass or machinery up and down the mountain. So this building that I think sort of looks like a Bond villain lair or something like that houses much more than the telescope. So you have kind of in the center part here, you can see the arrow pointing to the telescope itself, which weighs 350 tons, sits on top of a 16-meter telescope pier, and the dome itself is 30 meters. But then in this longer, more horizontal piece out to the right, you can see that there's a lift that is designed to be able to remove the mirror from the telescope, or the mirrors. And down in the lower right here, you have a clean room for working on the camera. So if the camera itself needs any kind of repair while it's in operations, you can just take it downstairs, essentially. And then you can also re-illuminize the mirror. So one of the things that happens with telescopes over a long period of time is that you have to sort of refresh the mirror. This is something that, you know, interrupts operations. It is, again, not easy to take something that is, you know, a mirror that weighs 75 tons up and down the mountain. So we can actually do it right here in this coating chamber that is located in the observatory. So this is really, you know, a huge investment, and it's a huge investment of time and community person power, and also of funds. And so this is really something that is built to last, and I think will be deeply affecting astronomy, not only when it turns on in a couple of years, but over time as well. So if we look at the telescope itself, so if you look carefully here, you'll see on that sort of yellowish platform, and then at the bottom of the foot of the telescope, there are these little weird androids, these little like robot dummy humans. And those are just to give you a sense of scale. I will also show you a picture of an actual human standing in the dome in a moment, so you can get a sense of scale too. So the mirror itself, the primary and tertiary mirror, is 8.4 meters, which is very big. It's around 27 feet, I believe. You'll see that there's this baffling around it and the structures that are around it, which means that the effective area, the area that the light shines on, is a little bit smaller, but still gigantic. And this gigantic thing that is 350 tons only takes 5 seconds to slew between different parts of the sky and settle and be ready for operations. And I know we have a lot of observers out there who, you know, are used to slewing across the sky with small telescopes, and it usually takes a lot longer than 5 seconds, especially with larger telescopes that are heavier and that move more slowly, that you have to be more careful with. But the Rubin Observatory is designed for speed. It's designed to tile over the entire night sky, or as much as possible within, you know, a single observing night or over a few days. And that means that you really can't be spending a lot of time slewing around. So it really is designed for speed. This is the support structure actually being installed in the last year. So you can see on the lift there, a little sort of cherry picker, there is a person who is doing some installation of the support structure. And this was something that we were very grateful to have be possible over the course of the pandemic. So obviously things closed down for much of winter in the Southern Hemisphere, meaning last spring and summer. But then once things were a little more open in the end of the year, with many safety precautions, so as not to have people get sick or to introduce illness into the area around the observatory itself, they were able to do some of the work. And one of the things they did was install the support structure. So this is the actual telescope with an actual human instead of an artist's conception, which is very exciting to see. On that neighboring part of Cerro Pachon, there's also what we call the Oxtel, or the auxiliary telescope. And this just follows LSST around as it's going through, as the survey is happening, and is able to take some calibration data as well as the observatory is doing its nightly observations. So I'll move on and tell you a little bit about the amazing camera that will help take these images and capture these images. You will see that the camera also has a special name, and that is the Department of Energy, or DOE LSST camera. It is enormous. So for scale, you could, if you are relatively small, you could probably stand in the middle of it, although we would not advise you to do so. The camera itself is 3.2 gigapixels. And has about a 9.6 square degree field of view, which I'll show you an example of in a moment to kind of give you a more intuitive grasp of what that means. But it reads out in 2 seconds. So again, if you're used to using telescopes that take 30 seconds or so to read out, more than that to read out, I certainly have spent most of my career with telescopes that do that, or cameras that do that rather. So 2 seconds is very fast. But again, much like the telescope itself taking 5 seconds to slew and settle, you are trying to be on the sky again between images as quickly as possible. And that's what allows it to tile over the night sky. So you really want this to be very fast. You will also be getting a multicolor view of the universe. So it has these 6 filters, 5 of which live at any one time on the telescope, that it has this filter wheel that you'll see here on the left, or an illustration of here on the left. And as it does its operations, it will, in practice, not be taking, a different filter with each visit to a particular part of the sky. So in practice, what it'll probably do is put on one filter and then tile over a certain part of the night sky, and then switch the filter, and then go back a little while later. The reason for that, because you could imagine, right, just like taking an image of the sky and then switching the filter and taking all of the colors as close together as possible. But it doesn't do that, actually, because that would create so much heat in the filter wheel. These are giant filters, which I will show you in a second. Remember, this this camera is nearly the height of a person across. So this would generate so much heat that it would actually be really deleterious to the health of the camera. And so the colors change over the course of the observations, but not kind of one in a row, like this GIF sort of implies. To give you an idea of how big of a field of view it is, this essentially is almost a 10 square degree field of view. To give you an intuitive feel for that, that's like 7 full moons across. And you can see an example of what that looks like in practice. That's in the upper left, Suzanne Jacobi, who has worked on the Rubin Observatory for many years. And it is all of these little individual detectors that will allow you to grasp a large fraction of the sky. So if you picture the full moon in the sky, then imagine 7 of those across and sort of filling up a circle with those. That's quite a big field of view. And so you can imagine that that's really important, right, to accomplishing its goal of being able to tile the night sky, being able to do so very quickly. Part of it is that you have this field of view. Part of it is that because the mirror is very large, it, is essentially a big light bucket. It captures lots and lots of light, so you can see very faintly. And then also you're doing this over time because your camera reads out in 2 seconds or your telescope moves in 5 seconds. So it really is an incredible machine. So we're anticipating that the camera itself, which is being built at Stanford, will arrive on the site in around 2022. In the meantime, this smaller camera, still very large by I think most people's standards, is what we call ComCam, or the commissioning camera. So one of the interesting things I think about just building a telescope that I think if you're not a professional astronomer, there's kind of no reason you would actually think about this, is that you're building not just, the building, you're not just building the telescope, you're not just building the camera, you're building all of those things together. It's really a system rather than a single object. And so all of those parts, including things like software that commands the telescope and that moves things, that records data, all of those things have to work together, right? The filter wheel has to work with the camera, has to work with the mirror, has to work with the dome, all of those things. So one of the things that we're doing over the course of the next year or so is delivering or is doing tests on the system, the parts that are there, like the telescope itself, with the commissioning camera, in order to test those pieces. And then they will swap in, that'll sort of troubleshoot the parts of the system that are built already. And then when the actual camera, the LSST DOE camera is done, that will be swapped in for the commissioning camera. And then they can go through all of the troubleshooting just with the camera itself. So you really are sort of, you think of it as like snapping together Lego pieces, but it's pretty complicated. So they all have to be talking and cooperating with each other in order to have a really functional observatory. Just to give you a very straightforward idea of how big these filters are, that's some technicians working with the filters, and you can see they're really very large. And that's kind of the family portrait as it stands right now. You can see over there the thing that looks like a dinner plate sitting on top of a blue table is the actual mirror of the telescope itself. It is sitting out there, and then on the left there, the sort of bluish cylinder with the black ring on it is the commissioning camera. And you can see just behind the mirror itself is the coating chamber, kind of behind those trusses, and some people for scale too. So I know that we all love talking about cool machines, but you probably are wondering what kind of data will actually be produced, because of course, we might like the machine, but we also love the pictures. So, it's the Hubble Space Telescope's pictures that are famous, right? Not so much pictures of the Hubble Space Telescope itself, although we like those too. So one of the things that I think is really essential to know, and that I mentioned at the beginning with respect to Hubble, right, is that Hubble has in part infiltrated and diffused through pop culture because its data is public, and because you can access that data, regardless of who you are, because essentially all of us, if you pay taxes, you own it. Now, this is actually true with the Rubin Observatory as well. All of the data will be public. Some of those international affiliates that we have as well, there are those individual institutions, and the scientists that are working on it there will also have some access to this, in addition to the Chilean community, Chilean astronomical community as well. So this will really be data that is kind of everybody's. And so I think that's a really exciting aspect of it. Now, one of the things you have to figure out, and I alluded to this earlier, is that when you have the telescope and you have the camera, even if they're all integrated together, right, you have to decide how to use it. And you can decide to do that a variety of different ways, right? You could imagine that you could take this giant telescope and just point it at one part of the sky and sit there and take image after image after image, almost like taking a movie. Or you could imagine tiling the night sky. And it turns out that what we'll be able to do, and we call this the observing strategy, right? Like, you're going to observe, what is your strategy going to be? Are you going to sit in one place? Are you going to look over the night sky? Which combination of different filters are you going to use? How long will you observe for? All of those things. So with the Rubin Observatory, one of the goals is to conduct what we call the main survey, often called a baseline survey, to And that's to really look over this 18,000 square degrees to uniform depth, which means that you have the same amount of depth in all of the images over 10 years. So in each, what we call a visit, in each sort of picture of the sky we take, it'll be a 30-second exposure, and then it'll go off and observe other parts of the sky, but it'll come back usually within an hour and observe that same part of the sky again. So that's where you're getting your time domain. So you're getting how the night sky changes over the course of not just, millennia, but hours. And in addition to this sort of main survey that it will spend like 90% of its time on, there'll also be these like mini surveys. And there's still, I think, some debate over what these mini surveys will be, but it might be that, for example, you might want to look at something that has been observed in another waveband. So one of the chosen mini surveys is to look at the Chandra Deep Field South. So Chandra is an X-ray telescope that has observed a deep field in the same way that maybe some folks have heard about the Hubble Deep Field, but that's in X-rays, right? So if you take the Rubin Observatory now, you can observe that same field and now be able to match up the things in X-rays with things in optical and infrared light, and you get a more complete vision of what is happening in that part of the universe. So these are still under debate, and there's still little tweaks to how we will actually do the observing strategy. And that's in part because it is a huge community effort. So this is just a sort of screen grab of a paper. That's a website at the upper left if you want to go read it for some reason. I know we have some very technical people who might be watching. So something for everybody, but don't feel obligated. But this is one example where we gather together a large fraction of the community that works on the Rubin Observatory and tried to figure out, right, like, what are the ways that we can use the telescope so that all of these different science cases, so everybody who's studying the solar system and everybody who is studying dark energy can use the same data to answer their questions. And it turns out this is actually like quite complicated to do. And it involves probably about as much diplomacy as it does, actual technical problem solving. And this is very much still a effort that is very much still in progress. So this is something that we're refining over time, essentially. Now, when the observatory is observing and producing data, there will be kind of these three kinds of data products. So one of the exciting things that Rubin Observatory does is it produces prompt data. So that means that anytime something in the sky changes, you will get an alert if you sign up for it, and I'll tell you how you could do that. You'll get alerts on things that change, especially like if they meet a certain criteria, say you like to observe supernovae or you want to see a comet or something like that. You'll be able to know whether something is changing in the night sky like within 24 hours. And that's really, really important because a lot of times when we want to observe either solar system objects or the transient universe, getting things early or getting them frequently so that you can like make better orbits is really, really important. In addition to that, there'll be data releases that happen sort of annually. And those are things that have, better processing done to them, that where you take many images and you add them together to give you deeper images over time, things like that. So then you'll have these sort of like, pristine data deliveries like in a big package once a year. And then in addition to that, there'll also be user data. So this is something that exists with other observatories and other missions like Hubble again, where, for example, maybe you took the data from a particular observatory and you made a catalog of which galaxies have certain kinds of like radio emission. So that catalog, for example, might be an example of user generated data if you were to like match it up with things that you observed with the Rubin Observatory. So these are sort of things that people produce within the community that the observatory itself doesn't produce, but they're like value added stuff. And so those will be also things that will be part of Rubin Observatory data. This is a very busy slide, but just to give you some idea of the scale that we're talking about. So the raw data from the Rubin Observatory is 20 terabytes a night. So that's all the sequential like 30-second images. Those alerts that you can sign up for, you will definitely want to filter them because there will be up to about 10 million per night. One of the things that will exist are these software programs called brokers that will allow you to do some filtering. So you will get comments, but not 10 million alerts. If you think we were talking about email right earlier, if you think a few emails are bad, then 10 million are probably much worse. So you probably want to put a filter on that so that you just get the things that you're interested in. By the 10th year, it's anticipated that the Rubin Observatory will have found 6 million new solar system objects, and that will be things that we have orbits for. So really over time, the 10-year data release should have that 37 billion objects in it, a 15 petabyte database. Phew. You might wonder how anybody is going to work with that data. So usually like if you're an astronomer that analyzes data now, you might like go to the data portal and you like download it to your computer, you do some stuff, you learn something about space, and then you write a paper about it. Well, once you get to the point where you're generating 20 terabytes of images a night, you're maybe not going to download all of that. You're hopefully not going to download all of that. And so that's where these data access centers come in. So what you're seeing here is another global aspect of the Rubin Observatory, which is that there are these computing centers that will serve up data to the entire world. So even though down here at the bottom of the globe, you can see the little pinpoint where the Rubin Observatory is located, all of Chile and the United States are actually connected by undersea fiber optic cables because there are already, there's very robust astronomy community in Chile. And so, the observatory is there doing amazing work. There's a long-standing collaboration between United States astronomers and Chilean astronomers. And so already a lot of data goes back and forth quickly between those places. And that's true of, across the Atlantic as well. And so you can see all these lines of different places in the world in which you'll be able to access the Rubin Observatory data. So this is sort of an idea where instead of, bringing the data to yourself, so taking observing something and taking an image with your own telescope and having it on your computer, this is something where all the data will live in these huge supercomputer centers, and you'll actually just be able to log in remotely and not have to have it on your computer at all. Now, one of the things that is very challenging about the Rubin Observatory is that the data will be really unique. It is not typical that we have images that go so deeply to such a large degree of the sky, which means that suddenly, parts of the sky where we might have had imaging in the past that is not so crowded will be extremely crowded because you will be able to see all of these new, very distant galaxies, for example. So what I'm showing you is a simulated image over here. And one of the things that people have been doing is simulating images so that we can test out like using different kinds of like data reduction and software on them and try to understand what the challenges will be. So this image here on the right is 1.7 millionths of a Rubin Observatory image, and you can see how many things are in there already. So this really, I think, will be very transformative for all of astronomy. To give you an idea of how people, including yourselves, might be able to access this data, there will be a science platform, which will essentially be a website where you can go to play with the data in the browser. So this will be something where you might be able to just go to a web browser and interact with Rubin Observatory data. There'll also be a substantial, there is a substantial effort in education and public outreach. So there will be like teaching tools and all kinds of ways you can learn about how to work with the data and how to observe it. And also, if you want something a little bit more technical, you'll be able to write your own programs to access the data and analyze the data yourself. Now, you're probably wondering, when is this cool thing coming? I've been wondering that for a long time too. It takes a very long time to make something as ambitious as the Rubin Observatory. And of course, the COVID-19 pandemic did not help. It is still ongoing, obviously, and so a lot of the safety precautions that are in place, or that were in place in the last year, which have been very helpful, some of those are still in place, but obviously, as people get vaccinated, it is at least possible to do more than was possible last year. So things are ramping up, but the delay does mean, especially with the fact that borders, if you need to like bring equipment or technicians across borders, obviously like you can go state to state right now, but it's been kind of complicated if you need to go to different countries, and that depends on who you are and which direction you're crossing, etc. So when you build a telescope, you have a team of people that you're employing to put that telescope together, and you obviously have invested a great deal of time in selecting the right team. And that means that, it means more money, it means more time, et cetera, because a telescope really is more than the sum of its parts. And it's really not just a piece of equipment either, right? It is the people that make it happen. So we were hoping that it would be a little bit sooner than this, but the target for full survey operations is sometime in early 2024, with around the beginning of April 2024 being the target right now. So this is obviously an evolving situation, but I'm hoping that within a couple of years, you'll be enjoying seeing all those amazing images in no time. So with that, I will conclude here, and we have a little bit of time for questions, I think.
Oh, thank you. That was wonderful. We actually have some great questions already lined up. If I could, I'll read one from the one of our viewers on YouTube. Is the mirror coating a specialized alloy to accommodate the near IR images?
Yes, I don't know the details of the coating, but if you look up the Rubin Observatory, there's quite a lot of information on the website, and I think it's still lsst.org for Legacy Survey of Space and Legacy Survey of Space and Time, and there's probably detailed technical information about the coating of the mirror on there as well.
Okay. Another question was, will the increase in orbiting satellites affect the operations? If so, is there a mitigation plan?
So the answer to will it be affected is yes, absolutely. The mitigation plan is kind of a question mark. So this has been, I think, a really big, kerfuffle, for lack of a better word, in astronomy in general, because these for people who are maybe not familiar with these mega constellations of satellites, there are several different companies, sort of most famously Starlink, that want to send up tens of thousands of satellites. And these satellites are visible. In some cases, they're visible to the naked eye. They are absolutely visible to observatories, especially like large professional observatories that can see things that are very faint. So, the LSST project, or the Rubin Observatory project, has been working with some of those satellite operators. So SpaceX has been, I would say, kind of the most cooperative in at least agreeing to talk. And there have been some changes. So notably, they experimented with sort of some new shades and coatings on the satellites, but that really did not do very much. It only decreased the brightness by less than a magnitude. And we're talking something that is like a naked eye object when it first launches, right? Which is big enough to saturate, that's bright enough to saturate the Rubin Observatory. And so there are different, because of the orbits and the angle of the sun, there are different times at night at which they're a bigger problem than others. But the best mitigation is to not have giant mega constellations of satellites. And this has been a really big debate, and I've actually done some work on this because one of the things I think that kind of is a stumbling block in this debate is that a lot of times astronomers look like they're sort of doing a not in my backyard thing, where they are complaining about getting astronomical data, but they're denying the ability of these operators to provide internet to the world. And one of the things that I, and in particular Meredith Rawls, who is a member of the Rubin Observatory project team and has done a very large amount of work on studying the effects of Rubin Observatory specifically. We wrote a paper with several colleagues that actually shows that the Starlink satellites are not actually cost competitive. They don't serve most of the world basically can't afford them or doesn't need them, even if they can afford them. So I would look up that paper if you're interested. The mitigation strategy is it's a difficult conversation, right? Because SpaceX would like to make money from the Starlink satellites, and kind of the best mitigation is not to have them. And they don't want to do that, right? Because they're interested in not having the ruination of the dark night sky be like something that makes them look bad. They're also not interested in not doing what they plan to do in the first place. So my sort of sense of it is that there's only so much mitigation that is going to happen, because ultimately they are interested in putting more satellites in space, which I'm pretty worried about, honestly, for a lot of reasons, including like the increased chances of collisions and like the, the possibility for increased space junk, how long it takes those satellites to deorbit, all kinds of stuff. But it is definitely a problem for professional and amateur observing as well.
Okay. Are there any other questions from our viewers on the Zoom chat?
Yes. Well, first, have you been to Chile?
Yes, not for some time now, but I was last there in 2017. Yeah.
Okay.
Yeah, and first there in 2001 actually was my first trip to Chile.
And the I guess the accommodations are rather sparse, or how is that?
Well, generally speaking, so I was at Cerro Chololo, which is another observatory, and generally you fly into Santiago and then you go up to La Serena. La Serena is a city. It's a beautiful city. It's on the ocean, as many things in Chile are, because Chile's got a lot of ocean. And it's a wonderful city. And then you in the case of Cerro Chololo, you go up and you stay in the observatory dorms. Observatory dorms are not typically very fancy at all, but I will say I have a number of dietary restrictions, and I was pretty worried because it's a big observatory and they provide meals for you. So there's a kitchen and they cook whatever they cook, and then like you eat whatever they cooked. And so in 2001, right, I'm like writing an email to the kitchen at the observatory trying to explain, what I can and can't eat. And I was like, I'm going to end up eating like dry bread for the entire week. And instead I got these like beautifully prepared, like huge, like cornucopia of food, like tailored to the point where I could barely like eat the entire tray. There was so much like delicious food. So I will say that the kitchens at Cerro Chololo are amazing. I don't think that there will be necessarily people on the summit with the Rubin Observatory, except for operators, fairly regularly. So if you're observing with Rubin Observatory, right, it's observing all the time. So you don't actually have to physically go to the telescope, and it's not like you could go in the dome, right? Like there's a 350-ton object that moves in 5 seconds. So you probably don't want to be in there. You probably won't be allowed to be in there. But yeah, definitely observing at Cerro Chololo was great. And I sometimes still think about those meals because they were fantastic.
That's neat. One other question. Funding. Now I saw the long list of supporters, sponsors, and I realized that when you sponsor a project like this, then you have some say in what is observed. But over a period, this is a 10-year survey, over a period of time, if all of what is coming and it's huge amount of data that's coming out of this, what's the incentive for the sponsors to just, if the information is free, what's the incentives for them to continue to fund it? If I were a third world nation and I had a great observatory and I can access this information, you'd never see a penny of my money. Yeah, my money wouldn't be any good anyway, because I'm a third world nation, but anyway.
So, that's an interesting question. So basically the entirety of the observatory and its operations and the like building of the camera and serving of the data and everything is all essentially, for the most part, it's the National Science Foundation, the Department of Energy. There were some private donations that made it possible to like do some early work on the telescope. But most of those things are coming through like giant national agency pots of money. The institutional contributors are typically putting their like membership fees towards a common pool of money that they can apply for. So the way it works in practice is that, the National Science Foundation and the Department of Energy are really funding the construction, right? But they're not funding like people who need to like work on stuff that's relevant to the observatory now before it's operating. So, that money from the member institutions gets pooled into a common pot that people could then apply for. For example, the Data Science Fellowship Program that I run got its first seed funding from that pot of money. So the incentive is essentially to do something for the common good. In the case of international affiliates, so because this was originally just the United States and Chile and participants in France, for the international affiliates, it's data access, right? So they are either contributing in funds or in what are called in-kind contributions, where they're doing something for the observatory, and that's what motivates them to continue contributing.
Okay, I know we have a hard stop in just 4 minutes. Are there any other questions by any of our viewers on the Zoom? I do have a couple more I can bring in real quick. Not hearing anything. Okay, 3.2 gigabyte sensor, 2-second download.
Yeah.
How do you do that?
It's mind-blowing, right?
That's nuts. And the other question is the sensor chilled? And if so, what gases are they using to chill, and to what temperature?
Ooh, that's a good question. I think it just uses liquid nitrogen. But again, I would consult some of the more detailed stuff that's on our website for the specs on that.
Okay. Yeah, the download. I mean, it's just, I'm thinking global shutter on a galactic scale, to just read everything out, and it's continuing processing, and it's shooting new photons over there.
Yeah.
So, something like that.
Pretty amazing.
It is. All right. Any other questions?
Yeah, we
John?
did have a question over here. Did you have to
Yes,
do
please.
anything to protect it from earthquakes?
Oh, that's a good question. I think the building design is pretty earthquake proofed, just because Chile does have earthquakes. But there's a lot of experience in building observatories within that zone, because there's tons and tons of observatories in Chile. But yeah, I think that's part of the consideration in the design of the dome.
It's a great question. All right, we're almost out of time here. I know that you have a hard stop. I want to personally thank you for being with us this evening and giving us an update on the project. And we're all waiting, certainly, for first light and the such, and hopefully in the future, once you start collecting some photons, we can circle back and talk again about some of the first findings that
we can show some actual pictures.
Yeah, that are actually being delivered. I got to believe that there's going to be some remarkable new things that are going to be found. I think of the impact when Pan-STARRS came online, and it's like, okay, but now this is just like exponentially much larger and much more timely gather. So it is our hour. We wanted to protect that for you. I know you have a hard stop, so I thank you. I hope everybody can applause and give you a thank you very much.
My pleasure.
for-
Thank you
for
so much
evening.
for the invitation. It's great
and
to
the
see you
time.
all, even
Yeah.
virtually.
Thank you.
Great. Thank you so
Okay.
much, Lucianne.
Thank you. Take care. Have a good night.
All right. Have a good night.
Bye now.
Len, you want to end the stream?
Yep, the stream has been ended.
All right.
And,
Thank you.